Hello, Calculus 12 students. Mr. Yoon here with another video for our Calculus 12 class. I posted on PCR that there's going to be a quiz this Monday, and this quiz will be one of the final things that will be added to your score for Term 2. Now, I just want to say that I was reading an email by Miss Evans that was sent to me by Miss Evans, and I believe Monday there might be a different schedule in the block order. So I think Monday might be a Friday class. So if you are in Kale and Lucas's class, you'll definitely have a quiz on Monday. And if you're in Haley Zabunka's class, then you may not have the quiz. So I'm just going to double check my email one more time just to make sure that we do have the proper block order in. Sorry, I'll check my email one more time to make sure what's happening. But just be prepared to write a quiz on Monday. And if you don't have class on Monday, then you'll have a quiz on Wednesday then. Okay, so anyways, for this quiz, I definitely want to test whether you can graph a polynomial using the concepts that have been taught in class. So for the quiz, there's going to be roughly two questions. The first question is, graph a function, and I will definitely give you a polynomial. I won't give you anything extreme, just a simple polynomial. And when you're graphing that polynomial, you want to find all your extrema, so any max or min points. And then you want to find any points of inflection. That means when your second derivative is equal to 0. And once you find your second derivative, I'll probably ask you again to find the levels of intervals of concavity. And it's also very good practice to find your x and y intercepts when you're graphing polynomials, because that will definitely help you put together the final sketch of the graph. And also another question that I will ask you is a question very similar to example number 3 on page 198. Alright, so I did a very similar example in the class notes, and the textbook also has a very similar example, so make sure you know how to do the example on page 198, because that will definitely be tested as well. Okay. Now, for your quiz, basically, when you come into class, I'm going to give you 20 minutes, so you need to get to work pretty quickly. And I will also allow you to bring a scientific calculator, okay? So if you're not very good at crunching numbers in your head, then I will allow you to bring a scientific calculator for this quiz. So if you have one, go ahead and bring one, all right? All right, so let's get started with some examples. I want to graph two examples and then call it a day. All right, so here's a example question that you could see on your quiz. I could ask you to graph something like f of x equals to x cubed minus 9x squared plus 24x minus 10. Okay, so a very basic polynomial. Let's go ahead and analyze this and sketch this graph here. Now, step number 1, I always recommend you to go ahead and find the intercepts. All right, so this doesn't require any calculus concepts. So go ahead and find your x and y intercepts. Now, just by looking at this graph, I know that negative 10 here, that's going to be my y-intercept. So my y-intercept is going to be at 0, negative 10. So I can find that just by eyeballing the equation. Now, finding the x-intercept is a little bit harder because you have to take this whole expression here and you need to set this equal to 0. Alright, so everyone that's taken pre-calc 12 now, you do have the knowledge to do this. Unfortunately, finding the x-intercepts takes a long time because you got to do long division here and use the rational root theorem. If you can't find the x-intercepts easily, just skip the step and move on, okay? We don't necessarily need the x-intercepts in order to produce a decent sketch of the graph. So if you can find the x-intercepts easily, great. If you can't, move on. Okay, great. So if I do ask you to find the intercepts, just tell me the y-intercept and then just say that the x-intercept is too hard to find, okay? And that's it. Second step, let's go ahead and find the first derivative, so f prime of x. Alright, so this should be pretty easy now. This will be 3x squared minus 18x plus 24, alright? So there's your first derivative, and once you find your first derivative, please set it equal to 0 so that you can find your critical numbers. So whenever you set a derivative equal to 0, go ahead and factor your derivative expression, because once you factor things, then finding the critical numbers is generally not too hard. Okay, so this is a very simple polynomial that I can definitely factor. So this is going to be x minus 4 and x minus 2, and therefore my critical numbers are x equals to 4 and x equals to 2. Okay, now what I'm going to do here is I'm going to go ahead and find, since these are my critical numbers, I want to go ahead and find the critical points. So I'm going to take this critical number and insert that back into my original function. So f of 4 is going to be 6, and I'm not going to show all the steps for that, so please try that on your own. And f of 2 here, f of 2 is going to be 10. So what this means is this means that my critical point here is going to be 4, 6, and my critical point here is going to be 2, 10. Okay, so these two critical points here, these are my critical points, CP, critical point. Now I don't know if this is a max or a min yet. In order to do this, you can use your first derivative test, but I'm not going to do that right now. I will show you another way to determine whether these are max or min points by using the second derivative test. You don't have to use the second derivative test, but I realize that sometimes I don't use the second derivative test as often as the first derivative test, so I will show you how to use the second derivative test in the next few steps here. Okay, so let's go ahead and now evaluate the second derivative. So I'm just going to draw a little line here, red line, and evaluate my second derivative. Remember, the second derivative will help you find your inflection point. So my second derivative here is going to be 6x minus 18. Now obviously if your first derivative is wrong, then your second derivative is wrong, and if that happens, you're pretty much going to get a 0 on the question. Alright, I do expect that you should be able to find the proper derivative, especially if I give you a simple polynomial, right? So if you can't get these derivatives right, then it's just going to be a 0. Alright, so after that, let's take the second derivative and set that equal to 0. And as I mentioned before, you always want to factor your derivative expressions here when you're setting them equal to 0. So this would be x minus 3, and that means x equals to 3 is the x coordinate of my inflection point, right? I'll just say IP for short. So that just basically means, once again, that's the x coordinate of my inflection point. And if I want to go ahead and find the real inflection point, I need to evaluate 3 back into my original equation. So f of 3 is going to be roughly 8. Okay, so this means that this implies that the point 3, 8 is my real inflection point. And I'm going to go ahead and erase this other inflection point just not to confuse anyone. So this 3 is that 3, and that 3 is that 3. Okay, so the point 3, 8 is my inflection point. Okay, so what I want to do next is, when I found my critical numbers here, and now I'll highlight the critical numbers here in this blue yellow color here. I don't know if those points are max or min, so what I'm going to do next is I'm going to apply the second derivative test. And the second derivative test implies you to do, basically, in order to use the second derivative test, you take the x coordinates of your, you take your critical numbers and you insert those back into your second derivative. And if you get a positive number, that means you have a minimum, and if you have a negative number, that means you have a maximum. So if I evaluate f double prime of 4, which is one of my critical numbers, this is going to be 6 times 4 minus 18, and this will definitely be positive. This is greater than 0, so that means you have a min there. Okay, so the point 4, 6, this is a min, M-I-N. And if I evaluate f double prime of 2, so this 2 right here is one of my critical numbers, and if I plug that into my second derivative, this is going to be 6 times 2 minus 18, and that's going to be less than 0, so this will be a max. Okay, so the point 2, 10, that's going to be a max. Alright, so this is another way that you can determine whether your critical points is a max or a min by using the second derivative test. So this right here is called the second derivative test. Now, you don't have to use the second derivative test if you don't want to. You may use the first derivative test. I just want to show you the second derivative test in action just because I haven't done a lot of examples in class with it, but there you go. There's your max and your min points. Okay, so let's go ahead and find the levels of concavity now. So if I draw a number line here, so if I'm looking for the intervals of concavity, I'm looking at my second derivative, and my second derivative is 6 times x minus 3, so that means my inflection point is at the number 3, and if I look at the right hand side, if I put a very big number in there, this will be positive, and you know, this side will be negative. So that means you're concave up. So CU means concave up when x is greater than 3, and your concave down, CD is concave down when x is less than 3. Okay. All right. So now we have enough information here. Let's go ahead and do a sketch now. So brand new page here. So let's do my sketch. I know I have a y-intercept at 0, negative 10. So that's the very first thing I found. I have a maximum point at 2, 10. I have a minimum point at 4, 6, and I also have an inflection point at 3, 8. Alright, so there's my key points. Let's go ahead and produce a simple sketch. So here's my XY axes. Here's my y-intercept here, 0, negative 10. So maybe this is going to be my maximum point there. My minimum point is at 3, 4, 6, so a little bit lower. So because I have a max, I know I'm going to have that kind of behavior there. If I have a min, I know I have that there. And then I also have an inflection point at the point 3, 8. So here's 3 in between those two guys. Okay, so let's go ahead and put this all together here. I mean, this is a max. It's probably going to go through... if I put this together here at this point, sorry, my max here is 2, 10. So max behaves downwards. It's going to go through this inflection point. It's going to go through this minimum point, and it's probably going to curve back right up because that's what a minimum does. And then the last thing you want to do is you want to connect the tail end of this maximum point right through your y-intercept, and there you go. So there's a very simple sketch of my graph there. And let me just zoom out for a second here. One more thing that you could do to just kind of verify that things are looking good here, this is your inflection point at 3. Just test your second derivative here, so f double prime of x. This was 6 onto bracket x minus 3. I know that this was 3, this is positive here, and this was negative. And I'm just kind of doing this just to make sure that my answer is correct. So I'm concave up when x is greater than 3, so here's 3, and everything above 3, it looks like that does represent a concave up type of picture. And if I look at my concave down situation, this looks to be concave down, so I can feel pretty good that this is indeed a very good accurate sketch of my polynomial, and that would be full points there. And if you want to go ahead and label your points, this isn't necessary, but you can do this to kind of just make everything neat here. Alright, so there it is. There is my sketch of that polynomial, and that would be full points. Alright, so I'm going to move on to my next example now. And sorry, one more thing I'm going to do before I leave this example is I'm going to delete this, and you know, in this question, I didn't use the first derivative test. I just used the second derivative test just because I felt like it. But if you are someone that's more comfortable with using the first derivative test, you know, what you would do is you would set up your first derivative, f prime of x, and f prime of x was, it was 3 onto x minus 4, x minus 2, and your critical numbers were 2 and 4. And if you want to use your first derivative test to determine whether the points 2 and 4 are max or mins, you may set up a number line and do the first derivative test. I'll just do this really quickly just for those students who feel more comfortable with the first derivative test. The reason why I use the second derivative test is because once you have like more than one critical number, then you have to do several interval points. So I decided to just do the second derivative test because it was a simple polynomial. But if you wanted to use the first derivative test, you know, just find some numbers that are bigger than 4, like maybe 10. And if you plug in 10, this will be positive. If you plug in a number between 2 and 4, like 3, well, if you plug in 3 into this expression right here, that's going to make everything negative. And that means you have a, you know, you're going down then up, so that gives you a minimum point at 4. And when you're less than 2, like 0, then this whole expression here will be positive. Alright, and that means you're going up and down, so you have a max at 2. Alright, so there's another way to verify that you do have a max or just by that you can verify that at x equals 2 you do have a max, and at x equals to 4 you have a min. Okay, so if you don't want to use the second derivative test, go ahead and use the first derivative test. It'll still give you the same answer. Alright, let's move on to the next example here. This one will be a little bit longer. So that probably means the question that you have on your quiz will be long as well. So for the next example, I will do y equals to 8x squared minus 16x to the power of 4. Alright, so once again we need to graph this, and we need to find all the max and min points, the point of inflection, and we also need to find the intervals of concavity here. Okay, so in order to find the x and y intercepts, let's go ahead and find the y-intercept first. So let's set x equals to 0, and that means my y-intercept will be at the point 0, 0. Okay, and for my x-intercept, this means we want to set y equals to 0. So that's the same thing as 0 equals to 8x squared minus 16x to the power of 4. Alright, let's go ahead and factor this. This is going to be 8x squared. If I factor that out, I should get 1 minus 2x squared. And that means I have x-intercept at x equals to 0. And if I set this expression equal to 0, that's going to be a little bit more, gonna do a little bit of work there. That's going to be 1 equals to 2x squared. 1/2 equals to x squared, and that means x equals to plus or minus 1 over root 2. Okay, and this implies that you have an x-intercept at x equals to 0. So there and there. So you do have you do have 3 intercepts there and 1 y-intercept. So a little bit of work there to find your x-intercept. Okay, I'm going to go ahead and erase this now. Once we found our x and y intercepts by using algebra, we're going to go ahead and find the first and second derivatives. So this will be y prime. This is going to be 16x minus 64x cubed. And then we need to take our derivative and set that equal to 0. And this one we need to factor once again. I can factor out I guess I'll factor out a 4x. If I factor out a 4x, I get 4 minus 16x squared. Alright, so once I factor my derivative, I can find my critical numbers. So this expression right here will mean that means I have a critical number at x equals to 0. And this part here in blue, if I set that part equal to 0, I'll just do a side calculation here. That's going to be 4 equals to 16x squared. 4 over 16 equals to x squared. That's 1 over 4 equals to x squared, and x will equal to plus or minus 1/2. Okay, so that means I have critical numbers at x equals to 0, x equals to 1/2, and x equals to negative 1/2. So I have 3 critical numbers this time. Alright, so with 3 critical numbers, that means more work. But before I evaluate the first derivative test here to determine whether those are max or min points, let's go ahead and find the actual critical points. So f of 0, taking my critical number, and these are my critical numbers. taking my critical numbers and putting them back into my original equation. If I do that, I get 0, so this means that this will be the point 0, 0. That's my first critical point. Then I'll evaluate f of 1/2. This will be 1, so this means I have another critical point at 1/2, comma 1. And if I evaluate f of -1/2, and don't worry, I'll give you, you can use your scientific calculator here, so if you can't crunch all these numbers very quickly, don't worry about it. You know, you can still find your critical points with the scientific calculator there. Okay, so that'll be -1/2 and 1. Okay, so just give me a second. I just need to think. I just need to kind of look through this and make sure all the numbers are correct. Okay, so that looks correct. So now that I found my critical points, all this is my critical points, my CPs. I'm going to go ahead and I'm going to use a first derivative test now to find whether these are max or min points. So I'm not going to use the second derivative test this time. I'm going to use the first derivative test. Okay, so here is 0, here is 1/2, and here is -1/2, and this is f prime of x, and that's going to equal to 4x times 4 minus 16 x squared. Okay, so if I evaluate the interval to the right hand side of 1/2, and if I pick a number like 10 or a million, if I plug that into here, this interval will be negative. Okay, so since that interval is negative, there's a 95% chance that the next interval will be positive, and then it will be negative, and this will be positive. Okay, so for my example, I know it's going to work out like this, but when you do your quizzes and your exams, go ahead and take the extra 30 seconds and check whether those intervals are indeed positive and negative. I know that they are, so this will be a max here, this will be a min, and this will be a max. Okay, so if I put those results back to my critical points here, at 0, 0 I have a min, so this is a min, M-I-N. At 1/2, comma 1 I have a max. That's right, M-A-X, and at -1/2, 1 I have a max as well. Okay, so there's my first derivative test. I've used it and I confirmed that I do have some max, 2 maxes and 1 min at my critical points. Alright, that's done. The next part is we need to go ahead and find the second derivative. And you know what, if you don't feel like going through all these steps, if you want to do this on your own, that's great. You can try on your own and just check your final answer with my final answer or your graphing calculator, and you know, you don't have to go through this whole video if you don't want to. Alright, so there's my second derivative. That's just taking my first derivative and using like the basic rules there. This one I'm going to factor out a 16, so the numbers here, they're not as obvious, but you got to play around with this, so make sure, yeah, you do bring your scientific calculator if you don't want to do all the numerical calculations. I do factor that, and then I can set that equal to 0. And if I take my second derivative and if I set that equal to 0, I look at that point, sorry, that expression right there. That's the same thing as 1 equals to 12x squared, because I'm saying this equal to 0. So x is going to equal to 1 over root 12 plus or minus. Okay, so I have 2 x values for my second derivative, so that means I have 2 inflection points. So once I take my second derivative and set that equal to 0, I take those points. I'll call this the x coordinates of my inflection point. Let's go ahead and evaluate those points at at f of 1 divided by root 2 and f of -1 over, sorry, this is all wrong. This is 1 over root 12, and this will be -1 over root 12, and I'll put this minus sign here just to make sure that sorry, a minus sign there. And I would go ahead and use your scientific calculator here. This is going to give me roughly 5 over 9, 5 over 9. So that means my inflection points are 1 over root 12, comma 5 over 9, and -1 over root 12, comma 5 over 9. Okay, so those are my inflection points. let's go ahead and just make up an interval to test where I'm concave up and concave down. So this is f double prime. Actually, you know what? I'll do that at the very end. Let me graph my let me just graph my function, and then I'll test my intervals of concavity at the very end of this video. Alright, so let's go ahead and write down our key points, and then we'll go ahead and sketch our graph. Alright, so let's put the graph together here. I'm going to go ahead and just kind of organize all the key points that I've found so far in my question. So the point 0, 0, this was a minimum point. The point 1/2, 1 was a maximum point. The point -1/2, 1 was a maximum point. My inflection points were plus and minus root 12. 5/9 for my y coordinate there, so this is your inflection point. Alright, and then I also had, at the very start of the question, I also had an x and y intercept at the point 0, 0, so this is the x and y intercept. And I also had an x-intercept, two x-intercepts at 1 over root 2, plus or minus, right? So those were my x-intercepts. Okay, so those are all the key points I found by taking my first and second derivatives and also just finding the general x and y intercepts. Let's go ahead and produce a graph here. And as mentioned before, I'll do my intervals of concavity at the very end just to kind of verify that my answer is was correct. So I have let's do the max and minimum points. These are generally the easier points to kind of graph. So 0, 0 is a min. 1/2, 1, so maybe this will be 1/2 here. This will be negative. Sorry, this will be maybe about there. Maybe this will be negative 1/2. So over here and about there, roughly. Sorry, that's not accurate, but give me a break. Okay, so here's a min, so I need to have a minimum will kind of go like that. Maximums will shape up like that. Okay, so if you kind of just think about this, it's probably going to connect like this, like that, and then you're probably going to go downwards like this, and downwards like that. Okay, so right here is my max at 1/2, 1. Here's my another max at negative 1/2, 1. And I guarantee you that this point right here is going to be your x-intercept, which will be 1 over root 2, 0. This point right here would be negative 1 over root 2, 0. And the last thing I'm going to do is I'm just going to check my intervals of concavity by drawing a number line underneath my sketch here. So here's my second derivative, and that's going to equal to 16 bracket 1 minus 12x squared. That was my second derivative after factoring, and my inflection, the x-coordinates of my inflection points, those were 1 over root 2, sorry, 1 divided by root 12, small number, and 1 over root 12 as well. 1 divided by root 12. Okay, so those numbers are between, so those numbers are less than 1/2, and you can verify that with your scientific calculator there. But if I pick a number to the right hand side of 1 divided by root 12 and plug that into my second derivative there, so that's going to be negative. And then if I plug in 0, sorry, if I take a number in this blue interval, like the number 0, that's definitely going to give me a positive expression there, and this is definitely going to be negative. And what that means is if I highlight this part right here in yellow right there, the concave down, that means from here onwards we're concave down, and that does match. And then that blue region means I'm concave up, which looks about right. And then I'm also going to highlight this part in purple here, meaning I'm concave down. This part does indeed look like I'm going concave down, so I can definitely celebrate because I know my graph looks right. Finally, just say that you're concave down when x is less than 1 over negative root 12. and when x is greater than 1 over root 12, and you're concave up when you're between those inflection points. Sorry, this last example was long and brutal, so that probably means the question on your quiz will be long and brutal as well. Okay, so there it is. There's my sketch of my polynomial right there. So those are the kind of questions that you could expect to see on your quiz next class. Now, I do have one more special announcement to make in about 10 seconds here, 10 or 15 seconds. I need to take a short little break and just gather my thoughts. And just stay tuned for a very special announcement. Okay, so I apologize that this video was long. Usually these calculus videos, I can't really make them 5 or 10 minutes just because there's so much algebra to do. I hope for those students who didn't want to stay and watch the full, half an hour of the video, I mean, that's fine. Just look at the question, do it on your own, and just verify that your answer is correct with the answer that I have as well. There's one last thing I want to talk to you guys about, and that was, there's one last little piece of information that I wanted to kind of share with the class, and that was regarding homework for Calculus 12. And with chapter number 5, in my opinion, I feel like more than half the students in the class, they're probably not keeping up with the questions that I put on PCR or the questions that are in your note packages. And that's unfortunate because the next time I see you, I'm going to have a homework check. Okay, so the next time I see you, we're going to have a quiz, and I'm going to ask you guys to hand in your purple booklets, your purple workbooks at the start of class. And while you're doing your quiz, I'm just going to go through your purple workbook, and I just want to verify that you have been keeping up with the homework questions that have been assigned for chapter number 5. Okay, and I'll probably verify that you're keeping up with the questions from chapter number 4 as well, and 3. I just want to make sure that you're making a decent effort in doing the problems that I've assigned over the course of the year. And if you have, then you're probably in good shape. If you haven't, here's the news here. If you haven't been keeping up with your homework, and don't get angry about this because I'm giving you fair warning. So if you watch this video, you're giving fair warning. I'm going to make sure that your mark goes down by at least a full percentage point if your homework hasn't been up to date. Okay? I feel like I've been very nice in this course, and I feel like a lot of students are kind of being lazy at times and not trying their best, but I do expect homework to be completed. So yes, next time I see you, I will be doing a full-on homework check to make sure that your work has been completed. If you haven't completed your work, guess what? You're probably going to lose a full % on your overall score. Now, last night I was at the school. Friday night I was at the school, and I was walking through the ground lounge, and there was one of the Calculus 12 purple workbooks there. And I was looking through that purple workbook, and I noticed that several of the homework questions were not completed. So I hope that student can get that purple workbook as soon as possible and finish all the homework questions, because if you don't, you're probably going to lose a full percentage point. Okay? And I don't want to call out anyone here on YouTube and through these videos, but that person was Connor Anderson. So you know what, Connor, you better get your workbook as soon as possible, and you better make sure your homework questions are all complete. And that goes out to Reese as well, and Hugh, you better make sure your questions are complete as well. So if those questions aren't complete, then justice will be pretty painful. All right, so hope you guys have a good weekend. I will not have a good weekend because I'm back at the school, but I hope everyone else is having a great weekend, and we'll see you guys again next class. Thank you very much for your time. Goodbye.